Welcome! Short version of the introductory video to the new chapter Quantum Physics. We start by giving a brief overview over the late 19th century physics, what the problems were. According to the classical and very well established theories of Newton's mechanics and Maxwell's electrodynamics, atoms should be unstable. Because you see, when you have an electron moving around the positively charged nucleus, let's say on a circular path, here the electrostatic force, the Coulomb force between nucleus and electron acts as a centripetal force, so the electron is accelerated all the time. And by classical electrodynamics, accelerated charges radiate away energy. So the electron would lose its energy, its kinetic energy, by radiating away electromagnetic waves, and in a very, very short time it should spiral into the nucleus and the atom would be gone. So this shows that the classical theories are not suited at all to describe atomic or subatomic processes. So we need a completely new theory. But this was actually not how it all started. It all started when physicists were looking to describe what is called the Blackbody Radiation using the classical laws of thermodynamics and electromagnetism. Very roughly speaking, a black body is a body that absorbs all incident electromagnetic radiation. Approximately realizing by building a sphere, painting it black and making a little hole inside the sphere, and the inside should be reflecting, like made of glass or metal or whatever, so that whenever electromagnetic radiation comes in, it gets reflected in all directions, and because this hole is so little, it's very unlikely to get out again. Then, when this body reaches a thermodynamic equilibrium, meaning that it has a constant temperature, then it radiates away part of the incoming energy as a thermic radiation. And physicists were trying to find a formula describing the so-called spectral radiance, which is roughly speaking the power that is radiated away. We are not going into any details here. Now, if you measure this, the real curve should look somewhat like this. At a constant temperature of, say, 5000 kelvins, the absolute temperature, and here's the wavelength, then the power distribution should be somehow like this here. Here we're in the ultraviolet region of the spectrum, and here we go into the infrared region. And two physicists named Rayleigh and Jeans had found a law using the classical theories, and this predicted that this radiance should be proportional to 1 over the wavelength to the 4th power at a constant temperature, meaning that as the wavelength approach 0 or the frequencies go to infinity, the spectral radiance should go to infinity as well, which is of course completely absurd. Remember, this is the power that is radiated away, so it can't go to infinity, whatever here the details are. So this was a big problem known as the ultraviolet catastrophe, because when going into the ultraviolet region of the spectrum, the theory gives me infinities. Then the German physicist Max Planck found 1 year later the exact formula describing this process of blackbody radiation. The exact formula involves some constants, of course the wavelength and the temperature, and here's an exponential function. Details again are not important, only that this law is contained as a special case when the wavelength get larger. Then also this classical formula gives pretty decent results for the actual curve. Here you see rough sketches of some of the curves for 5000, 4000 and 3000 kelvins. Here shaded is the visible spectrum. And this coincides perfectly with the measurements, with the experiments. So this formula is true. Now in these constants, Planck found there is a new constant, which is very, very tiny, 6.63 times 10 to the minus 34 joules times seconds. And this is nowadays famously known as Planck's constant. And it turned out this constant actually governs all the subatomic or atomic processes. Now, to derive this formula, Planck had to make a very strange assumption, which he at that time thought was merely a mathematical trick to make the math work. It couldn't describe the physical reality because it was so absurd. He had to assume that the energy exchange between the electromagnetic radiation field and the so-called oscillators in the wall of the black body, they didn't call it atoms yet, the atom hypothesis had yet to be confirmed, but there needed to be some kind of oscillators that could react to the electromagnetic radiation and then reflect it or absorb it. And he had to assume that the energy exchange is not continuous, but discrete, or as he called it, quantized, meaning that electromagnetic radiation energy can only be emitted or absorbed in discrete packets, which Planck called quanta, singular quantum, and these packets carry away the energy or give away the energy E equals h, this famous Planck constant, times the frequency, or which is the same for electromagnetic waves, speed of light divided by the wavelength. And this actually was the birth of quantum theory. Without Planck knowing it, he had a hard time accepting it for the first, I think, even years after his discovery. And this means that the energy exchange here between the incoming electromagnetic radiation and the black body can happen in a packet of 1 times this quantity. Let's assume for a given frequency, this here is about 10 to the minus 19th joule. Then the energy exchange can happen in this package, or 2 times this number, or 3 times this number, but it should be impossible that energy of 1.5 times this here is transferred, or 3/4, or even a half. So if the energy is less than this here, h times f, it shouldn't be possible at all to interact with such an oscillator and to make it oscillate and send back electromagnetic radiation. To demonstrate how absurd this is, let's use an analogy. Say, for example, I have a box of chalks and then I take them out and measure them. So I find a chalk of this length, now corresponding to HF. Then I take another chalk and I find out, well, this is 4 times this length. I still find another chalk that is 2 times this length, but it is impossible to find a chalk that is 1.5 times this length. Yeah, you see, this is completely, absolutely ridiculous. But it turned out to be true and was actually, as I said before, the birth of the modern quantum theory. And Einstein and Bose, Indian scientists, later realized that these quanta are actually real physical particles, which are nowadays called photons. They turned out to be the quanta of the electromagnetic field. And here particles is not to be understood in any classical way. They are not little bullets flying around. We're going to discuss all of this in detail, but this was a quick introduction to the birth of quantum physics. Thanks for watching and bye-bye.